Okay, so good morning to everyone. You go on the OpenSees GitHub repository, which is where the OpenSees code is. We also try to implement new elements, like, for example, a new shell element, because the shell elements that were available in OpenSees had some problems about large deformation, so we decided to implement this one. It is still in the pull request, so it should be implemented soon inside the code, but it is already there. Basically, we improved the way the shell element can handle nonlinear kinematics, as you can see in this example, very large deformations, finite rotations, as in this case. And this new shell element is very effective also for the study of crack propagation. Then other than this, you have all the new OpenSees elements that have been implemented in OpenSees version 3.2, plus a lot of other features inside STKO. I will not talk about them now because you will see them while I will do this example. Okay, now regarding how I will handle this webinar, in all the previous webinars, we have basically, the webinar were lasting about 2 hours, but then we noticed that people start losing focus, so we will try to make this webinar a little bit shorter. What is about this webinar? It is about modeling of infills, measuring fields. But I'm not going to talk about all the ways that are available in literature for implementing infills. I will just talk about how to implement one of them, one of those methods inside STKO, and how you can use, or actually how I used the Python interface of STKO to create an automation that allows you to create these infill assemblies in a very easy way. So probably you are familiar with the infill model that I'm going to talk about. As I said, there are many ways of doing it, but I will use basically the model proposed by Mosalam. In fact, there is an example on the OpenSees example manual, which is about modeling of infill wall that takes into account both the in-plane and the out-of-plane behavior, and the element removal. I forgot to share the screen. Oh, here it is. Let me share my screen. Okay. Let me go full screen. So as I said, we will talk about the infill wall model by Professor Mosalam. This one is one of the many ways you can use to represent infills. We're not going to model infills as a micro model as we did in previous webinars. We're going to do instead we're going to model them as macro elements. In this particular case, the infill is modeled as a diagonal beam, which is actually 2 beams with a central node, because this one is actually used to represent the out-of-plane behavior. And then I will talk a little bit about how they implemented this one inside the example that you have here. And I will show you how we implemented the same thing inside STKO. And of course, here you don't have only the concept of infill modeling, but also the concept of element removal, which is something that you can do in OpenSees. You can do it both in TCOL, for example, if you want to remove elements using custom conditions, or you can do it as they did inside the C++, inside C++ code. Okay, so now the basic focus on this webinar is to show you how this kind of modeling that may seem simple, it's actually very complicated to implement inside a TCOL file. Now imagine if you want to use OpenSees without a user interface. You will see that there are many calculations that you have to do to compute the equivalent properties for this wall. And there are a lot of lines of code that you have to write in TCOL just to write one single infill wall. Now imagine that if you have to model a real-life structure, this one became soon very time-consuming, probably impossible, and very error-prone. And instead, we decided to create an automation in STKO that basically allows you to model the infill as a single 4-node quadrilateral element. You just will need to provide a material model that I will show you later on and an element property model. You assign it to them, and then STKO will do all the calculation to produce a post-processing file which is exactly the same as the one provided by Professor Mosalam in that example. And this one is very useful if you want to implement your own customization, because you waste a little bit of time at the beginning, but then you have that tool for all the analysis that you want to do. Okay, so let me start with a new file, both in the post and in the preprocessor. Okay, now before doing it in STKO, I would like to talk about this model and to show you how you can run it from the source code provided on the website. Why? Because this example is quite old. So it was working with the previous versions of OpenSees, but if you try to download the code and run it with the current version of OpenSees, you will see that there are some errors. So I will explain you how to fix them. And of course, you will find the fixed files when we will upload them in a few days on our website. So first of all, you go on this web page and you can download all the input files. There are all the links down here and all the instructions. Let me go down. Here, you have all the files. And then you have these PDF files that is a summary of all the calculation they did for computing the equivalent properties of the measuring field. Now I put all those files inside a folder called reference. And basically this file is, well, this list of files, there are many things here that are used for material, units, so all the utilities. But the main files are two. The model IR, which is this one, that basically builds the entire model. Actually, I already have it open here. Okay, model IR. Let me move this one. I will need it later on. Okay, so this one is the first model, is the first file that you have to source. And basically now we'll give you just a summary. It starts by creating the main model. Since the structure is very simple, they did everything in a loop. So they prepare rigid diagram and so on. These are quite standard things. Then when they arrive here, down here, let me go, okay, here they start creating things for the infill walls. And here is where things get complicated, because here, for example, you can see a fiber cross-section for the out-of-plane behavior of the infill, and you see a series of parameters here that you don't know where they came from, but actually I will show you. So for each infill wall, you have to create a fiber cross-section with certain properties that comes from lengthy calculations. Then, after you have this fiber cross-section, you have to create an elastic section for simulating the pinnet beams that are here. Let me show you these ones. Here. Okay. And then, once you have them, you have to create basically the mid-side node with the out-of-plane mass. And then you have to create two beam with hinges elements that are this one and this one. And also in this case, the elastic properties of these beams comes from other calculation in order to simulate the stiffness and the entire behavior of the masonry wall. Not only this, you don't have only to create the elements, you also have to create the recorder called collapse, because basically these recorders will allow OpenSees to remove those elements and that node when they reach a certain criteria. So as you can see, for a single wall, you have to write all these lines of code. They are not that much. There are a few lines of code, probably 100 lines of code. The problem is that the calculation behind those lines are very lengthy. And if you download the calculation file, you will see that it is a PDF of a MATCAD file. And you can see that there are many lines of computation. These highlighted are the user input. And then you have a huge amount of calculation to be done. Well, they actually are based on FEMA 356. And there are a lot of calculation that are used finally to compute the properties of the equivalent fiber cross-section. I will show you, I will go quite fast here. Then if you're interested in the theory, you can see this one is well documented, so you really understand what's going on here. But then all this calculation, some of them also involved solving nonlinear equations. At the end of this, you obtain all the properties for the fiber section. So the yield stress, the equivalent yield stress for a steel 0-1 material. They use the same strength in tension and compression because they use just one diagonal. And then also the equivalent area of each fiber is computed according to certain criteria, and the same for their location. So as you can see, just to obtain this, you have to do a lot of calculation. Now keep in mind that doing this by hand, it's really complicated. So now first I will show you how to run this example so that we have a base results to which we can compare. Now keep in mind that if you try to run these files as they are, so as you download them from the website, you will see an error. The main error is that in previous version of OpenSees, as you probably know, the fiber cross-section had an optional value for the GJ, for the torsional constant. It was optional, so you could use it or not. It was not important. In fact, in their original file, this one was not here because then they add the torsional strength using the section aggregator. And this was perfectly fine with the previous version of OpenSees, but with the current version of OpenSees, if you don't put the GJ constant, OpenSees will throw an error. So basically, the only change that I did was to go through all the fiber cross-section and add this GJ constant, okay? This is a change that they made in OpenSees and they did not document it. That's why people still think that GJ now is optional, but with the current version, it's not optional, it's mandatory, okay? So just remember to fill this value. And then I did a very small change, which is not mandatory, just to add the MPCO recorder. So that since this file has not been created in STKO, you can add the MPCO recorder manually so that we can see the output of this file inside STKO. Then if you want to run it, when you are here inside the reference model, I created another file called main TCOL that first sources the model IR, because this one basically builds the model and runs the gravity analysis. And then this one does a first model analysis, computes the Rayleigh damping, and then it runs a transient analysis, okay? So basically you source the first one, you source the second one, and then I simply created a batch file to run the analysis using the OpenSees that I have installed in my computer, okay? So you just call OpenSees and you run, you pass the main file. So it will source both of them and it will run the analysis. Okay, so now let me run this one. It will take about 2 minutes. And in the meantime, I will show you how you can start this. So basically, you will find here Convergence Issue, but they use an adaptive time-stepping techniques to solve this problem. Okay, so we can wait a couple of minutes so that it finishes. It should be at, 40 seconds. But in the meantime, while this one will finish, I will show you how you can start the same model in STKO. Basically, we need this one just to have a reference solution. Okay, so instead of wasting time on building the model from the beginning, I will provide you with the initial file, which is called infill model, that has all the entire structure modeled exactly as the TCOL file provided by Mosalam, but without the measuring fields, okay? So you basically can copy this one, and I will put it here, so I create another folder so that I can start from 0. Example. So when you will download all this file, you will find this reference model, and this reference model has everything but the infills. And we will start from this. Okay. So basically, this one is the model. I will explain you a little bit what it is and the parallelism with their file. So basically, you have a structure model, which is a polyline. I've shown you how to model it in previous webinars. So if you are not familiar with STKO or how you can model frame structure in STKO, you can see our previous webinar. So you have three geometries. The first one is the structure. And the other two are the master nodes, one for the first floor and one for the second floor, okay? Then you have an interaction. This interaction is for the rigid diaphragm. The interaction, when you create it, you can select the two master nodes as masters, and then all the vertices of the two floors as slaves. Then we need three definitions. The first one is a linear ramp. It is a linear time series that will be used for the gravity loads in the gravity analysis. And then we have two path time series. Why two path time series? Because in the original file, here in the reference, they provide you in the GM files folder two files with the earthquakes. Okay. Then they use a procedure to read those files and put it inside STKO. I did this to put it inside OpenSees, but I did the same, just opening this one and copy pasting the values inside STKO. Okay. And so you have them here. Keep in mind just one thing, in the TCOL file provided by them, the structure is oriented in the XY plane, okay? And so the X direction is in the Z global axis. Here instead, I modeled it in the XY plane as the plan, and the elevation is in Z, okay? So here you have two time series, where I basically put all those values, okay? One for the X direction, and one for the Y direction, okay? Then all the material properties are taken from their models, okay? So a concrete for the core, for the cover, the rebars, then you have the fiber cross-section for columns, and the same for fibers, for beams, sorry. Then once you have these two fiber cross-section, you need the beam section property, as you probably know. So you choose the fiber cross-section and you choose an integration type. So once you have them, this one has been assigned to all the columns, as you can see. Probably it's better if I go here. And all the beams have been assigned to all the beams and girders. If you look at this file, the original file, they distinguish between beams and girders, but actually they assign the same properties to them. That's why I created just two sections, okay? Now, all these elements are basically forced beam columns. So I created just one forced beam column element with linear kinematics. They were not using any P delta or rotational effect. So I just created this one, and this one have been assigned to the entire structure, okay? Now for the boundary condition. When you go in the original file, you will see that after they build the entire model, which is about here, yes, here. So they create all the nodes, then they create the rigid diaphragm. The rigid diaphragm is optional, but in the original implementation, there is the rigid diaphragm, so we put it in our model. Then they create all this fiber cross-section as I shown you, okay, and it is here. So basically, the boundary conditions are the rigid diaphragm assigned to the interaction. Then you have a pin at all the base nodes. As you can see here, all the base nodes have been selected. There is a pin, and then they also fix the out-of-plane rotation, but this is not important actually. Then, of course, the master nodes are not attached to the structure, so you have to fix the degrees of freedom that do not take part in the rigid diaphragm. As you know, the rigid diaphragm constrains the in-plane displacement and the in-plane rotation, but the other 3 degrees of freedom remain free. So the master node should be fixed in those remaining 3 degrees of freedom. So the out-of-plane vertical deflection and the 2 out-of-plane rotations. Then you have to assign the masses for columns, beams, and girds, and in this case they were different. Okay, so these values are provided inside the original file. So same thing for beam and for girds, and then the loads. Every load have been assigned as a beam uniform load, and if you see, this one is basically, this value is just the mass times the gravity acceleration. And for beams and girds is the same, but not along the x-axis, but along the z-axis. And these basically are all the boundary conditions assigned to our model. So once you have all the boundary conditions, you go to the analysis step. So the first one is our recorder, similar to the one that I implemented inside the handwritten TCOL file. Then you add all the constraints. As I said, we have two single point constraints, the pin at the base and the fix of the master nodes of the rigid diaphragm. Then you can add all the vertical loads. We have just 3 of them, which are element load. Okay, so the load of the columns, beams, and girders. And then you can run the gravity analysis. Now here we basically have a static analysis. In this case, we have a transformation method, but I will show you that in the next example we will use a penalty because it's easier in the case you have overlapping constraints. So if you are not sure about the transformation method, just use the penalty. Just one note that I want to tell you. Typically, for the system, I always use a sparse solver like the UMF pack or the Super LU. This is perfectly fine because a sparse solver is fast both for small structure and for large structures. But since in this example, I'm going to use element removal, the element removal as they implemented for the infill wall, they will create problem with sparse solvers. So probably we are going to change the code because I realized that there was this mistake inside their code just when I was preparing this example. So it works, but it works with full solvers, okay? So just use the band general. And then you can choose whatever. Here I choose a Newton-Raphson as an algorithm, just 10 steps. Oh, and this one is, if you know STKO, this one is a new feature of STKO. In the previous versions, you always had a fixed time step. So you had to decide the lambda increment and the number of time step. Now in this case, we changed it because in many software, you do not decide the lambda increment. You actually decide the total duration of the analysis. For example, in my case, the static analysis should last just 1 second. And then I want a number of increment, okay? If you use the fixed time step. Otherwise, if you don't know if this analysis will converge, you can use an adaptive time step. And STKO will take care of this automatically. So this one is one of the new features, and you will see as I run the analysis. Then, of course, after the gravity analysis, I keep the load constant, and I reset the pseudo time step to 0. Oh, let me just change it to penalty. Okay. After this, I run a model analysis. Because basically we need the model analysis to compute the first and third frequencies, and then we use them to compute the Rayleigh damping as they did in their example. And you can see them here. Basically, once they finish the gravity analysis, which is the end of the first file here, they just run the gravity analysis, then they source this one. In this one, they first do an eigenvalue analysis. And also in this case, they use a full system, not a sparse system. And they compute the first and the third frequencies to compute the Rayleigh damping. So how to do the same thing in STKO? We basically create a custom script, and then we put here a code that we provided on our website. If you go on our forum, there is a topic about model analysis, and we prepared a file that basically does exactly this thing, so the model analysis, and writes everything in a file called mass summary, so that you can go there, read the values, and do something different, okay? Now after this, you have the Rayleigh damping command. Also here we provided a new feature, so now you can select directly the 2 frequencies that you want, then the damping on each phase, and then it will compute automatically from the frequencies and these values the alpha and beta parameters according to the Rayleigh damping. And now the alpha is just 1. For the beta, as you know in OpenSees, this beta can be applied to one of the 3 stiffnesses provided by the OpenSees element, which are the current one, the initial one, or the committed one. Now, in this example, they applied it to the committed stiffness, as you can see here. They decided to just switch on the dependency on the committed stiffness. So we did the same inside STKO, okay? Perfect. And then for the dynamic analysis, we need the dynamic loading. In this case, there are uniform excitation. So we created a uniform excitation in Y using the time series GMY. And same thing for the uniform excitation in X, okay? Then you have another feature that was not present before, which is called monitor. A monitor is basically something that allows you, by default, you have only this one, and will basically create a Python interface that gives you a summary of what is going on in OpenSees without looking at the console, because many of you probably are not familiar with a console. You cannot copy paste the values from a console very easily. So we decided to create a monitor, and you will see what it is. And optionally, you can create plots. So while the analysis is running, you can monitor what's going on inside the analysis. So for example, in this case, I decided to plot a graph that has in the x-axis the time step ID, and in the y-axis has the displacement of this selection set, which is basically the control node on the second floor. And I want to plot the displacement along the x-axis, okay? That's fine. And then finally, we have the dynamic analysis. So transient, still the penalty method. As I said, ban general, because otherwise it will not work. And then the Newton method, Newmark method. And as I said, since this one, as you have seen from the original OpenSees file, in this case, you have convergence problem at a certain point. In STKO, we choose adaptive time step. Now, in this case, you choose the total duration, which is 40 seconds as the time series. And then the initial number of increment, which is 2000. And now if OpenSees will find convergence problem, it will automatically adapt the time step size to find a convergence, okay? And here you have some controls for the adaptation. They're pretty easy, but basically it says how much the time step can increase. And in this case, I don't want it to increase. How much it can decrease. And of course, I want it to make less than 1, because otherwise I cannot reduce it, okay? And that's all basically. So now we can run, well, actually the reference analysis is finished. So I want to load the reference analysis so you can see what's going on there. And it's this one. And then we will run our own model. So let's use a surface plot. Let's switch on the nodes, and you will see what's going on inside this file. So at the very beginning, you will see that you have the entire structure plus the infills. Let me give this a slight deformation, and let's try to run the analysis. Now, if you remember, we created just 2 analysis stages. The first one, which is the gravity, and the second, which is the transient. But when you go in the output, you will see 4 stages. So you may ask, why is this happening? Because every time in OpenSees you remove an element, which is actually what's going on inside this example, OpenSees automatically creates a new stage, and the MPCO recorder recognizes it, okay? So let's run this example to see what's going on. So as you can see at the beginning, you have both of them, and then as soon as they reach some failure criteria, OpenSees will remove them, okay? Now in this case, they have been removed quite at the beginning. Okay, now we can stop it. We don't need to watch the entire video, okay? Let's go to the beginning, and I want to show you the same thing with the fiber cross-section, so you can see how they conceived the fiber model of this one. Let's go back to the beginning. Okay, now fibers for beam cell columns are pretty standard, so you already know them. Let me go to stress so you can see, okay, the location of the rebars. And then you can see what's going on inside an infill. Now I want to isolate this one to explain you how it works. Okay. So this one is the model of the infill. As I said, it is made of 2 elements. Each one of them is a beam with hinges, where here you have an elastic pin section. So an elastic section with an almost 0 out of plane bending stiffness. So it simulates a pin. Same thing here. Here you have an elastic section, a regular elastic section to simulate the elastic stiffness of the wall. And in this point, you have a fiber cross-section. This fiber cross-section has been made exactly to simulate the interaction diagram given by the FEMA. So all the description of how they implemented this thing is described here, as you you can see. So that's why you have these two strips of fibers. They have been located with a certain criteria. Okay. So let me show everything, and I want to extract the displacement. So surface color map, and I want to extract the displacement of the top node. So we will use it as a reference solution for our model in STKO. So we go in chart data, extract chart data on nodes. We extract from every stage using the time step ID, and I want to extract the displacement along the Z direction, because as you can see, they started from a 2D model in the XY plane, and then they just extruded. Okay, so the X direction, which is in STKO, is actually now the Z direction in the original model. Okay, so next, and we can call it UZ reference. Okay, so this one will be the reference solution in this direction, and we will use it to compare with our own model in STKO. Okay, so if you go back on our model, which is the same one as the previous one, but without the infills, we can use the monitor, as I said, to record the same thing. So we want to monitor the same thing, displacement along the what in STKO is our X direction, which is equivalent to their Z direction. And we can also use a background plot. A background plot is actually a plot used as a reference solution. So we can see if our solution is actually overlapping with the original one. So let's go a second to the post-processor. We go here and we copy the first column, Control-C, and then we go on the monitor, and we paste it here in the X-axis, okay? And then we do the same for the second column. Copy and paste it here. Okay. Okay, so perfectly. Now we can run the first analysis. Now I want to show you how to do the model, the damping based on the model analysis. Since it is not completely automatic, when you open this file, you can just go to model, and let's say, okay, before running this analysis, I want to set up the damping, but I first need to know the model analysis results. So I go here. After everything is done, I just throw an error, just because I need to wait, okay? So that we don't waste time running the dynamic analysis. So in this case, it will do all these steps. It will reach the model analysis, will do the model analysis, will save the output, and it will break, okay? So we can go and read the results and set up the damping accordingly. So let's go to the analysis and let's run it. So save it and run it inside the example folder. As I said, this one is the plot, okay? As you can see now, you have the standard OpenSees console, and you have the monitor that basically saves everything that happened to OpenSees. So you have the stage ID, the time step ID, the time increment, the total time, the number of iterations required, the last norm, and the percentage of the analysis. This is quite useful for monitoring what's going on. Then you have a plot, but this plot now is empty because we just didn't reach this point, okay? Because I throw this error, wait, okay? Now, actually, this file, this thing that have been written in the console, have been written inside the example folder, mass summary. So I open the mass summary, and you can find the frequencies for the first and second stage, okay? So basically, what I did was just to copy paste those frequencies inside the damping. Okay, so you copy paste the first and second one, which is not actually those ones. Okay, let me copy paste the others, which is mass summary. So I take the first one, which is not this one actually, is this one. So I take the first one. Where is it? Okay. First one. and the third one, because they use the first and the third one. Okay, so now you have these two values. You go back in model, and I simply remove the error that I put there to stop the analysis. Oops, I think I removed something. No. Okay. Let me save it, and now we can run the entire analysis. Now, as you can see, basically now you have the background plot, which is the one that we copy-pasted from OpenSees, from the original file on OpenSees, and this one is our solution. But actually, it is still missing the infill walls, okay? Now, we don't need to run the entire analysis. We can just stop it. Because now I want to show you how to model the infill now. Now, basically, as you have seen, okay, let me remove this one. And let me go back here. So I go to property. I save this one. Now, basically, as you have seen from their files, which is this one, modeling an entire infill takes a lot of time. So imagine to do this one in STKO. I go here and I model all these fibers. It will take a lot of time because I have to do all this calculation. So now I will show you how we implement it inside STKO. Now, for those of you who are not familiar with this, everything in STKO that goes from definition down to the analysis steps are actually Python scripts. So you have access to those Python scripts. You can change them, or you can create new ones. If you want to know where they are just in C, program files, STKO. Then you have a folder called external solvers, and here you have a huge amount of Python files, for example, for element properties, for physical properties. So all those Python files, for example, let's go in one of the uniaxial material. They just describe the way this material model or this element or this condition have been implemented inside STKO. Okay. So what is the point now? I decided not to model directly the infills as they did, because for me it is too much complicated and very error prone. So I decided to do something different. In a new version of STKO that you will find, you will see that you have a new material model called infill wall material, and a new element model which is called infill wall element. And basically I implemented it just by remove this one. Okay, you have these two files basically that you can find under physical properties, special purpose, mesory infill wall material, and under element properties, special purpose, mesory infill wall element. Basically these ones, well, actually the material is pretty simple, and I will show you now how it works. So now that we have this file, you can save it with a different name, and I call it infill model complete. And we are going to add the infills. Now, how I thought I would like to model them. It is very annoying to model the infill as an assembly of beams with particular cross sections. So I thought that it was easier for the user to create just quadrilateral elements in STKO, and then create a script inside STKO that automatically takes this quadrilateral element, takes the properties from a material model, and creates the equivalent diagonal element, as they did in their computation. So basically what I did is to go here in their calculation. I just copied all the calculation inside this Python file, as you can see here. This one, sorry, for the element. I took the entire calculation, and as you can see, it take a lot of code. So for example, the first thing that I do is to create a unit system, because in some of those calculations, some formula are unit dependent. And as you know, STKO is unitless, so we need to make sure that whatever input you put, it will be translated into key pinches inside this calculation. Then we take all the properties from the material model, as you will see later on. Then we take the sizes of the length and the height of the masonry wall directly from the geometry inside STKO. So for example, we take a reference to the document, We take a reference to the element, we make sure that the element is a 4-node element, we take the 4 nodes, and then we compute, for example, the length and the height of the element, okay? While in their example, this one should be an input from the user. Now imagine, as you can see here, for example. Now imagine if you have to model a lot of infills that have different sizes. You have to go through this file for every infill, and it will take a lot of time. Instead, STKO can take advantage of the Python scripting. So basically, I take this thing from STKO, and then from here down to the almost 500 lines of code, we do all the calculation. And all these calculations are basically used to compute the equivalent here. All the properties for the fibers. So the yield stresses for each fiber, the strains, the yielding strain for each fiber, the area and the location of each fiber. So basically everything you have here, it will be written, it will be computed in the same way here. So for those of you who are interested in Python coding, you can have a look at this file. Now, once all the calculations are done, STKO starts to create this assembly. So while inside the preprocessor it is a 4-node element, STKO will create the same assembly that you found in the original file. So for example, if I first write a comment, then I start creating the fiber cross-section, then I do a loop on all those arrays that I created to just create the fibers. I do the same thing for creating the elastic section, for the pin connection. Then I create a node that was not present in STKO. As you can see here, you don't have any node inside this. And STKO will automatically create this node in the middle. It will compute the normal of the wall to assign a mass. So in this case, for example, you can also create an infill wall which is inclined with respect to the global axis. Once we have done this, it creates 2 beam width hinges element, and it also creates all the recorders for these elements. As you can see, for each element, you have to create many files. So you have at least 3 recorders plus a file for the out of plane, in plane diagram. So there is a lot of work. But once you code it, and it took me 2 days to do this one. So it is 2 days. Probably if you are not expert with Python, for you it will take something more. But once you have a code, Python code inside STKO, you can reuse it how many times you want. And the nice thing is that once you do your model, it will be pretty fast. Now, for example, imagine you have this model without infills. If you want to add infills with this tool, it will be very easy. Now you will see that we can do it in a couple of minutes, basically. So the first thing that you have to do is to prepare the geometric model. So as I said, inside STKO, this model will be assigned to a surface element. So how do I fill these holes with faces? Now, the first thing that you have to do is to create a construction line down here so that we close these holes. And then we do the same on this other side. So bottom to bottom point. I did it because I need to close this area. Then we have a command which is called planar, which is basically used to create planar surfaces from a grid of lines. So I select on planar, and it says, okay, select everything, and I switch off the entire selection, so I have only edges. And I select all the edges lying on the same plane that will be the boundaries of my elements. So right click, and as you can see here, you have your 4 faces in a new geometry. Now we can do the same for the other side. So I switch off the entire geometry selection. I select all the lines, right click, and escape for unselecting, okay? Now that we have these faces, we can get rid of these 2 lines that we created just to, select and select. Now these 2 lines down here have been used just to construct the faces, so we can remove it by pressing cancel. Perfect. So now what we have? We have a structure, we have these 2 master nodes, and we have these 2 planar faces. Now keep in mind that if we keep the geometry as it is, the 2 walls will be detached from the structure. Now we need to perform a Boolean operation to join the faces with the frame structure, okay? So we can just go here You go under Boolean operation and you click merge. When you click merge, there is an option, okay, perform intersection, which is what I want to do. And STKO tells you to select all the geometry that you want to merge. Now, in my case, I want to merge the structure with these two faces, this one and this one. So as you can see, they were 3 separated geometry, right click, and the output will be one merge geometry, which has both the frame structure and the surfaces. Now what happens if I go in property? Okay, now in this case I've been lucky. In this case, all the properties have been maintained, but it may happen that due to the order in which you construct something, it may happen that you lose some of the assignment. But if this happens, you can just go and reassign something, okay? But almost every time STKO is sufficiently smart to understand what was the previous selection, okay? So in this case, just to make sure, we have the physical properties on the columns and on the beams. Same thing for the element. Let's go in boundary condition. All the boundary conditions are the same, basically, so that's fine. Okay, what else? Let's go in property. Now, the only thing that do not have a property are the infills. So what we did now is just to create the geometry for the infills. So as any other element, we first need to create a physical property. So we go here, add, and we can call it infill material. We go under model, and this time we go under special purpose, because of course the infill is not a precise material, it's not actually a real material, it's a material for a special purpose element. And you can find it here, measure infill wall material. And here you have these properties which have the exact same name that you can find in the original file and in the calculation file, okay? So it's easier for you to understand what they are. Here I kept also the same description that they have in their calculation file. So for example, the first one is the Young modulus of the masonry. Then this value is the expected compressive strength of the masonry. These two values are related to the strength of the bed joints. Then you have parameters for the wall. So the thickness and the self-weight, the weight density of the infill bricks. And then there is under miscellaneous, you can find the force units and the length units. Why? As I told you, STKO is unitless. So you can model in whatever dimension you want. You just need to be consistent. In this case, however, they use some, if you go on the calculation, you can see that they use some formula coming from the FEMA, which is not unitless. Some of them are actually unit dependent, and they need to be in kip inches. So that's why we decided to do, okay, let's say that the user models everything in kip inches, so the entire model, you can just keep it as it is. If you decide to model in, I don't know, Newton meters, you can just go here and say, no, I model the forces as Newton and the length as meters. In this way, STKO will understand that your input is not already in kip inches, so it will do the translation. Now, in my case, I just use kip inches, so it is fine to keep it as it is. Now, the default values are actually the values for this example, so I don't need to change anything. If you want to change something for your model, you can just play with those parameters, okay? So this first value are the one related to the material models, and that's fine. So now I want to assign this one to all the faces here. So if you want to select all faces, all the subfaces of a geometry quite quickly, you can go under the geometry, you can expand it, and you have something for selecting each and every face. Or if you select this one, as you can see, you select all the faces. So right click and select. Once you have them selected, you can just drag and drop the infill material. Okay, so now as you can see, you have the physical material assigned. But if I go in element property, visualization, they are still transparent because I didn't create any element property for the infill. So now I can go under element property, right click, add, and I use an infill element. Then you go under model, special purpose, and you can find measure infill wall element. Okay. Now, in this case, you have few parameters that you have to choose. The first two actually are really annoying for me because they're actually the properties of the surrounding reinforced concrete members. Unfortunately, those equations that they use for computing the equivalent properties for the masonry infill, they depend on the surrounding reinforcing concrete members. Now, for the moment, I decided to leave to give the user the freedom to choose these values. I know it is quite annoying, so probably before I release the new version of OpenSees, I will make STKO find those values automatically. But for the moment, the user should input it, okay? And those are the same values found that you can find on the example. Then you have the number of interaction points, and as described on their documentation, it should be an even number, okay? So for example, if you choose 6, you will generate 10 fibers and so on. Now 6 is the exact same value that they used, so I kept 6 here. And then there is this value, which is the expected compressive force. Now, once again, this value at the moment should be input by the user. Probably what I will do is to try to understand what is the compressive force coming from the first vertical analysis and then assign it automatically to this element. But I still have to work on it, okay? So as you can see, the parameters are really few. You don't have to do anything. Basically, you create an infill material, an infill element. Now I want to assign the infill element, so I can go on infill material, I can select it, and so I use the selection to drag and drop the infill element. Now, as you can see, all the operations that here were basically 500 lines of operation, in STKO are translated as just creation of 2 elements with few parameters, almost I think 10 parameters, and just a drag and drop, as you can see. Okay, then STKO will take care of converting everything. Now, once you have done this, so we created the surfaces, we merged everything, we made sure that all the assignments are properly done, we create the infill material, we create the infill element, and we assign it. Now, we don't have to do anything else to this. We just go on the mesh. We go on mesh control because now we have faces. So we have to make sure that they will be meshed as quadrilateral, because by default, if I try to mesh this one, you will see that they are triangles, okay? And it will not work. So I go on mesh controls, I select faces, and I want to make them structured and quadrilateral and linear because I just need the 4 node elements, okay? Then I select all the faces and I click assign and done. So when I build the mesh now, they are just 4 node elements, not triangles, okay? So once I've done this, I can save it. And I can finally run the last analysis. Okay, here I probably made some mistake here with the model. Yeah, probably I missed some of the masses here. Well, let me see if all the masses are properly assigned. Columns. Yes, probably I didn't assign them, but this is what happens. Okay, now let me open the file that I will send you, which is the complete one, which is this one. Okay. So same model as I did before, because probably when I was building it, I didn't assign masses. So just to be fast here, I go here and I run the analysis. Okay, run it. Okay, so now we can see our plot with the background plot. Actually, you will see some differences now from the original file, but I will explain you why. Those slight differences are due to the fact that basically, while I was building this model, I realized that in their calculation, and that's why I tell you that doing everything by hand is error prone. They used as the height of the masonry wall 140 inches, and as the width of the masonry wall, they use 120 inches. But actually, if you go, and so basically these two values are used to compute all the parameters for these models. But actually, if you go on their model, they're actually used different dimensions. So for example, if you go on the very beginning on this file, you will see that they are not matching. In fact, let me see where it is. Okay, the height of the column is 14 feet, which is actually 168 inches. And same thing for the length. It's 24 feet, which is about 688 inches instead of 120. So those small values, those few differences are due to the fact that they basically mismatched the dimension that they give in the computation and the dimensions that they used in the model, okay? Instead here, STKO is computing the parameters right from the geometry, so they are correct. But the differences are not so high, so probably the walls were not doing so much. So the analysis is almost done. We are at 85% of the analysis. Let's wait a few seconds. And then we can go in the post-processor and see the results. Okay, finished, so 100%. We can close this one, and we can close the OpenSees console. So now, as you can see, while here it was a continuous model, so just 4 node elements, the post-processor is actually exactly the same as they did. So if I open the database, not in the reference, but in infill model, I have this one. Okay, so let me first show you the surface color map. And then I also want to switch on the nodes. Okay, so in this stage, 2 already failed. Let me go to the beginning. Okay, so where we have all the infills. And let's try to run first animation. Okay, they start like this, and then when they reach a critical time step, they just fail. Okay. Now, as you can see, the top one didn't fail with respect to the original model, because actually the material properties are different, because they were using material properties coming from smaller infills. That is one of the reasons why having an automation is better, because you avoid those mistakes. Okay, so we can also see what's going on with the fibers. As you can see now, they are slightly thicker here because we are using a larger infill with respect to what they did. And also in this case, for example, I'm plotting the fiber stresses. Let's say we want to switch off the steel, which is material number 3, so we can see the stresses here much better. And let's see what's going on at this level. So you can see actually what's going on inside each one of them. So the fiber cross-section is actually very useful to understand what's going on in concrete members in real time. Okay, and of course, then we can go back in the surface plot and we can extract all the outputs that we want. So for example, in this case, I want to extract the displacement along the y direction, which is the same one we were monitoring. So stage 1, well, actually I want to extract it from all stages along the x direction against the time step ID on the top node. Next. And this one is ux. Okay. We can do the same for the displacement in the other direction, because we also applied an earthquake in the other direction. So I keep the selection, and instead I want to plot it along the y direction. Uy. Okay. Now let's say you want to see what's going on inside one of those walls. So you can go back to the beginning where you have everything. And let's say I want to export this one and this one. At a certain point, this one will disappear. So I will show you what happens when you try to export a graph from something that has been removed from the OpenSees analysis at a certain point. So you go to chart data, results on nodes, all the stages, and I want to plot the out of plane displacement. So in this case, it is along the global X direction. Next, next. Now in this case, there are two variables, and I use keep multiple results, so I don't want to sum them. And we can call it of plane of infills. Okay, now you can see the first one is moving like this, but at a certain point here, it reached a failure point, and then from then on you see 0, because actually STKO is not able to extract anything else from that point, because from that point on, that node is not yet in the model anymore. While this top wall was still in the model, so STKO was able to extract everything from there. You can do the same thing for fibers. For example, we can see what's going on inside one of the fibers there. So let's go in. Oh, we can see the bending moment, but it didn't extract it. So let's go on the fibers. We can see what's going on inside one of them. So for example, inside this fiber. So we're going to extract your data and extract from sub-element Gauss points, so fibers. And section fiber strain against section fiber stress, we can export, oops, use a result, section fiber strain. Oh, we have a question. I will answer soon. Just let me finish this one and then I will answer the questions. So section fiber strain against section fiber stress. Perfect. Next. Next, and we can call it infill sigma epsilon. Okay, so this one is the behavior of one of those fibers. And so on. So basically, once you have the STKO model, you can do whatever you want once you have the output. So that's why we didn't save so many recorders as in the initial file. We just need the MPCO recorder, and then from that you can export everything you want. Now, for example, in this recorder, I forgot to save the section where it is section force, section deformation. But in this case, for example, you can export also section force and deformation. Actually, I think I did not forget it. I think I have it. So let me go and see if I plot Gauss point. Yes, I have it. Okay, so I can isolate this number, for example, plot. Oh, I want to show you another feature. Let's say I want to isolate these two members. Show. This one is a new feature inside the new version of STKO. As you know, there are two beams, okay? And both of them have the last Gauss point at one of the ends of the beam, okay? So in this point. So how do I know what I'm selecting? If I click here, I have actually two overlapping Gauss points, one coming from the element on the left and one coming from the element on the right. Now, someone basically asked us to implement what is called particle shrinking. So for example, when I have this situation, I can use a shrinking factor, like for example, 0.1, so that you can see now the particles are basically moved towards the center of the element. If I put 0.2, as you can see, they will move. So now it's easier for you to select those elements. If I go on the front view, probably it's easier for you to understand what I'm saying. Okay. If I put 0 as default, they are in the real location. If I put 1, which is the other maximum, they all collapse to the center. But if I put a small value like 0.2, they will be just moved toward the center. So it will be easier for you to select those being at the same point. So for example, we can select this one, and we can have a look at the bending moment along the local Y direction, because this element has the Z direction pointing towards. So we want to see the bending moment. No, actually about the Z direction, yes. So we go in extract chart data. This time we want to extract something from the Gauss point. So next, all the stages, and we want to plot section force deformation versus section force. and we want to plot KY, I think it's KZ, then we see if it is not that, we will change it, against MC, next. And this one is the moment curvature of the wall. Okay, it's this one. So you can see actually what's going on inside your model at every level. So you can extract nodal values, you can extract Gauss point values, and fiber values. So this is pretty much everything. Now we have some questions. So someone is asking, I just wonder if you have come up with any convergence issue for this example, especially if we push it enough to show nonlinear behaviors, how you deal it through STKO. Is there any automatic way? Yes, there is. In fact, when I was running their example, there were convergence problems, and they decided to implement this kind of adaptive time stepping, which is not actually an adaptive time stepping. They just do the analysis. If something goes wrong, they just change the algorithm. So they start with Newton. If something goes wrong, they try Broyden. And if something goes wrong, they try Newton with line search, or someone else also tries Newton with initial tangent, and so on. Oh, it is here, Newton with initial tangent. Actually, I prefer to keep the algorithm that the user wants, and instead I want to use adaptive time stepping. This one is one of the new features that we have in STKO. As I told you, if you go in the preprocessor, and if you go in dynamic analysis, you can see that here, I decided to use an adaptive time step, while by default you have a fixed time step. If you're not sure that the analysis will converge, just use an adaptive time step, and I will explain you how it works. So basically, you choose the total duration of your analysis, which is 40 seconds. You choose the initial number of increments, that in my case was 2000, because with 2000, I have the time increment, the exact time increment of the time series, which was 0.02. And then I said, okay, but I want, if I have convergence issues, as I had in this example, I want to try to reduce the time step. I don't want to change the algorithm. I want to keep it as the Newton one that I used, but I want an adaptive control of the time step. And how it works. You basically choose a max factor. This max factor is if you are converging very fast, how much you want to increment your time step. And in my case, I choose 1 because I don't want a time step larger than the initial one. Then there is this other factor that is saying if you have convergence issues, how much you want to reduce your time step, because of course you cannot reduce it without any limit. And so I say, okay, if my time step reduces by more than this factor times the initial time step, the analysis will stop. And then you have 2 other factors which are used to let the algorithm decide how fast or how slow it should reduce the time step. Because keep in mind that when you do dynamic analysis, since it is a time integration scheme, it is supposed to be a uniform time step, okay, a uniform grid in time. So when you try to reduce the time step, you should do it quite slowly. So I said, okay, my increment factor at most can be 1.5. So I cannot increase the time step more than 50% every time, okay? So the point is now, how does this one translates into the TCOL file generated by STKO? Is this one basically. If you go in analysis steps, you will see that when I go to the very end because it is the dynamic analysis. Okay, so here I set up the dynamic analysis. Now in the previous version of STKO, you would have seen just analyze, then the number of time steps and the DT, okay? So the standard command from OpenSees to run a fixed number of time steps. Now in this case, we didn't do that. We just said, okay, do a while loop, and then in every while loop, try to run 1 step of the analysis with the current time factor. Then if everything is fine, then I check the number of iteration. If I'm converging very fast, so for example, if my number of iteration is 2, while I wanted 10 iteration, I can increase it. And I can increase it within certain limits, for example. I don't want to make it increase more than a maximum factor. I don't want to make it increase too fast. That's why I use the factor increment, which is this 1.5. So all these things are very useful to push the analysis right to the end. Otherwise, if something goes wrong, I just reduce the time step using the same concept. But in this case, I will have maximum number of iteration, which is more than the desired one. And so my factor increment will be less than 1. Then, of course, I need some stopping criteria. So if my factor is too small, and in this case, if my factor is less than the minimum factor, which is this one, then I have to stop. Otherwise, that while loop will go infinitely. Okay? And so basically this is all. As you can see, I didn't change anything. The Newton-Raphson is still there. So I just used the Newton-Raphson without changing to initial tangent or Broyden or any other alternative algorithm. I was just calibrating the time step. And then you can see many other things, because while we calibrate the time step, we call the monitor function. Then we print something on the output that is only for creating the monitor. But the concept of the adaptive time step is here, okay? And to have it, of course, don't forget to switch on adaptive time step. So whenever you think you have convergence problems, use adaptive time step, and it will try to. The default values are almost every time are good, basically. If you want to play with them, you can play with them, but those values are fine. So now, second question, how do you check out of plane behavior in infill wall? We structure response you record to check damage because of this behavior. Actually, this is done inside the recorder. This is another topic, actually. In what I was explained today is one of the many ways you have to model an infill. This one is the one proposed by Mosalam. Now, in this case, I'm not checking my own criteria. I'm using the recorder command, the recorder collapse command, which is, let me go and see, which is here in the elements. Oh, here you can see all the elements that I generate. So, for example, let me go to one of the infill elements. Okay. So, for example, this one is the infill element assembly coming from the quad element that in STKO was number 70. As you can see, I generate these fibers, I generate the elements, and then I generate 3 recorders called collapse. These 3 recorders has a particular criteria, and this criteria is basically checking a file called OOP IIP, which is out of plane in plane curve, coming from the FEMA calculation. So all the details for the derivation can be found here. But basically, when you do all these calculations, and then there are all the references. So if you are interested in understanding how they works, you can see this file. At the end of everything, here you have all the properties that STKO automatically calculates for the fiber cross-section. But above all, you have a file used for the criteria for the element. Let me show you. Okay, here I have all the fibers. And then there is this last calculation, which is calculating the in-plane displacement, out-of-plane displacement curve, which basically computes 2 arrays that gives you this interaction domain. This interaction domain is basically what the recorder wants, like in this case, which is this one. What the recorder wants to understand when one of these walls should fail and should be removed. And in fact, as you can see here in the example, STKO automatically creates one of these curves for each one of the elements. For example, this one was the quad number 70. And for the quad number 70, it generates this curve, okay? So this one, let's say, is the criteria that they use for removing the element. Now, there are many other ways that you can use in OpenSees and STKO to remove something. Now, in this case, I used the example coming from Mosalam. And in their implementation, they use this concept of the recorder collapse. So all the calculations are done inside OpenSees to understand if an element should be removed or not. In a future webinar, I will explain you how to do the same, but without using those recorders, but by using just Tcall functions that allows you to remove an element or a node or any other kind of OpenSees components. But since it can be done in Tcall, basically, you can choose your own criteria. Now, it was too much for the webinar of today, so I decided to postpone it in a future webinar. But of course, you have the opportunity through Python and TCode to specify your own criteria for removing the elements, if this is what you were asking me. So if there is any other question. If there is something that is not clear. Oh, when they will be available? Yeah. Oh, typically we provide videos, the recordings, and all the content files during the next days. So it should be tomorrow. But actually, since this model will work with the new version of STKO, it will be released in the next month, in the next week. So you will find it by, I think, Monday. Okay. Anyway, you will receive a newsletter. So if you are registered on our website on one of our webinars, you will receive a newsletter telling exactly when this new version of STKO will be available on our website. And then, of course, in the same day, you will find all the data for this webinar so that you can run it. Because actually, if you download these files now, you cannot run it with your own version. Okay. And then there is another new, when you will download in the next week the new version of STKO, we changed the licensing system. And so now with the new version, STKO will automatically tell you when there will be any update, okay? So for this first update, you will receive a newsletter. From then on, STKO will tell you every time there is a new update, and will suggest you to do an upgrade, okay? Okay, so any other questions or doubts? I see there one more question, but oh, there's another question about was private. Okay, when you do a question, put it to everyone so everyone can see it. Make wire. Not in this case, not. So this is a new question. Instead of merge, not a make wire. I will show you why. Let me share my screen once again so that I explain you the difference between make wire and merge. Okay, so back to STKO. Let me do a new file. So as Victoria was asking, there are many ways to perform Boolean operations, and I will explain you some of them. Because actually this one is one of the topics where people find it difficult. When you have two wires like this, for example, one edge, and then you draw another edge like this one, okay? So you have two edges that they share the same position of their vertices, but they're actually two separated geometries. So for example, if I mesh it, you can see that I'm generating two elements, but four nodes, not three, because here, these two nodes are separated, okay? So two disjoint geometries, it will generate two disjoint elements, so four nodes in total. Now let's say I want to join them. Now in this case, I can use both the make wire and the merge. Why? Well, the merge is pretty general, so the merge will merge everything. It's just a Boolean operation. The make wire is faster, but it works only with edges, okay, like in this case, and only when they share the position of a node, but not when there is an intersection. So let me explain. When I click on make wire, I select these two, right click. Now I have just one geometry, and if I try to mesh it, okay, I have two elements, but just three nodes, because this one is shared. Okay, so now the make wire actually gave me the same results of a merge. So if I click merge and I select everything and right click, the output is the same, just one merge. Okay, now let me show you something where the behavior is different. Let's say I have this one, and then another line here. Then I do a make wire. The output will be two separated geometries. Why? Select make wire, right click, and the output are two geometries. These two edges here have been merged into a single wire because they were sharing one vertex, okay? But these two, no, because they don't have any intersection, okay? The make wire is just used to attach nodes that are the same position, but they do not perform any intersection. The merge is different instead, because the merge is actually a Boolean operation, so it performs all the intersection. If I select the three of them, right click, it will be just one single geometry plus this intersection in the middle, okay? So what to choose, it depends on you, for example. Many times you want to join them and create the intersection point. Many times, for example, imagine you are modeling braces in a building and you want to join those braces with the surrounding frame, like this, for example. Imagine you have these two and then you have the surrounding frames like this. Then you want to merge everything without creating the central point, because otherwise this one will be, you don't want them to be attached here. In this case, you can use the make wire because it will join everything into a single geometry, but without creating the intersection in the middle. So these two elements here will be actually detached from one another, but they will be attached to the frame, to the surrounding frame, okay? If I do the same with the merge, it will be different. It will create an intersection in the middle, okay? Now the same thing, the same concept happens for faces. Now let me show you this one. If I have two faces, let me copy this one. Once again, I have two separated faces. This edge in the middle will be separated. In fact, for example, if I query the geometry and I want to see the free edges, so the edges that are not attached to each other, this one is red, okay? Now, if I do sew faces, which is pretty much like make wire, but it works only for faces, okay? So if I do like this, I select them, right click, and the output is a shell, which is actually a multi-surface, pretty much like the make wire. If I do the merge, once again, I have the same thing, same output. Now, what is the difference? In my example, I use the merge, not the make wire, nor the sew faces. Why? Because basically I was doing something like this. So I had faces, and I had also lines. I cannot do the sew faces here because actually I'm trying to merge entities of different types. I'm trying to merge faces with edges. So this, I cannot use the make wire because it works only on edges. I cannot use the faces because it works only on faces. In this case, I have to use the merge. The merge command is the most general one, okay? So I can do this, and the output will be a compound. A compound because it has both faces and floating edges, okay? With the merge, you can do something even more complicated. Like, for example, I can draw a line here in the middle. You can do a merge, and it will cut everything, okay? So it will make this one pass through the center. So this one is actually a real Boolean operation. These one are simplified operations, but that works only on specific cases, okay? Okay, so if there is any other question. How to use the command query geometry. If I want to know the length of the column beam, or can I change the position of it without delete the element? Okay, so once again. So the query geometry, actually changing the position of a node is not possible because we are not working on the concept of the so-called orphan mesh. So for example, when you work with the programs like SAP or Midas, you are actually working element by element, so it's easy to move a node. But in this case, it is a geometry. I cannot just move a node because moving a node of a face is actually changing the geometry of the face. So you just cannot do it like in any CAD. You can just redraw the element, okay? So moving a node is not possible unless it is a simple node like this, and then of course you can move it. Now, okay, how can I use the query geometry? Okay, so query geometry is basically used to obtain information on the geometry. So in the first thing, the first tab is the selection. This one basically allows you to perform selection in an easier way. For example, I want to select 3 edges, and it select this one. Why? Because 3 edges are edges that are shared only by one face. So for example, these edges here are the boundary of this face, but the edge in the middle is common between 2 faces, so it is not called free and it will not be selected. This is very useful to understand if a Boolean operation was correct. There is select floating edges. A floating edge is an edge that is not shared by any face. Like in this case, it will select the first and the last edge if I do select floating edge. Opposite from this, for example, you can find select internal edges, which is the opposite. You can select edges that are shared by multiple faces and so on. And then, of course, you can do other selection, like, for example, select by length range. For example, I want to select only entities that have a certain length or a certain area or a certain volume. Or select by location, for example. So these one are tools for rapid selections. Then you have another tab called property. Here you can query the length, the area, the volume, center of mass, and so on. So for example, if I want to know the length of this edge, I can just select this one and then query length, and it will give me the length of every selected edges and the cumulative length. Now in this case, I selected just one edge and it's fine. But for example, if I select 2 edges, or let's say I want to know the perimeter of this one. So I select all the edges, all the external edges of this one, and then I say query length. It will give me the total length of everything plus the cumulative length. So in this case, I obtain the perimeter of the entire geometry. Same thing for area, for volume, and so on. Okay, I can unselect it. Let me go to the next question. How did you connect the infill to element with central mass with the surrounding frame? Okay, let me open the input file again. Which is this one. Oops, I was saving. Let me reopen it. Open Infill World 4. Okay. So basically, once I finished my frame model, I just created a face, and this face was merged with the others. What does it mean? That the finite element coming from this face is actually sharing the same nodes of the surrounding frame, as I show you now in the example where I was using the merge command. So imagine that here I have a quad element and the surrounding frame, and they share the same node because of the Boolean operation. As you can see, they are attached. Okay. Now, since they share the same node, STKO then generates through this file. That's why it is done automatically, which is the measuring fill wall element. This is quite long, so I will try to explain it as fast as possible. But basically, every time when you run the analysis or when you write a TCOL file, STKO goes inside every one of these models. It goes into their Python file, and they call the write TCOL command, okay, with the current element. So what STKO is doing is taking the document. From the document, they take the current element, which is in this case could be this one, for example, okay, the first one. And then it queries the element, it makes sure that it is a quadrilateral, that it has 4 nodes, and then it takes the 4 nodes of this one. Now the 4 nodes of this one are the same nodes used by the surrounding frames. So then, after doing all the calculation at the end, when I create the extra node, let me go here. Okay, right, extra node. The extra node is not in STKO, but I create it directly in the tuple file, which is here, and I give it a tag called center node tag. Then when I create the two beam with hinges, I create these beams from the central node tag, which has been created automatically by STKO, with the node number 1, which is present in STKO, okay, which could be, for example, this one. And then I do the same with the other, and it is connected from center node to node number 3, which would be from center node, which will be here, connected to node number 3. And that's why they are all attached, okay? Because the initial quadrilateral element has been attached with the surrounding frame through the Boolean operation, okay? Is there any other question? Oh, the last question. Oh, actually, we have. Oh, there was a question by Vittoria that I missed. Gravity loads cannot be converted into mass automatically. Is this correct? So I need eventually to put them by hand. Same for the self weight. I need to. Yes, exactly. This is exactly what I did. Basically, I created both loads and masses. They are actually consistent in the sense that the load is the masses times the gravity acceleration. But at the moment, there is no automatic tool to do the conversion. Probably we will use it. We will put it inside STKO. This is a good suggestion. Another question. Do you have any future conditional plan of releasing source code of Masonry and the material model you create to official OpenSees repository? Actually, we are not sure about it because we are still publishing things on this model. So probably in the future, yes, but not now. Not now because we are still publishing and writing articles about this. Does the material model you created works more? Does Masonry material model you created works more bricks along the thickness width? I don't think I understood the question. Are you asking if you can model a multi-layer shell? I mean, if you do a micro modeling and if you do it with solids, of course it can. You have to model all the bricks. If you want to model it with a shell, it depends on the assumption because the shell assumes that the shell assumes that the behavior is the same. So of course, if you want to give different materials along the thickness of the shell, you can, because when you create the layer shell, you can create. Let me show you, for example. When I create, let's say, a physical property, let me create an ND material. Let's say damage TC3D with some parameters, and we call it ND brick 1. Then you create another one, and let me clone it, and let me clone it again. So this one can be the infill between the two bricks, for example. And then the second brick, let's assume it is different, for example, and the brick 2. Let's say it has a different material. Then when you create a layer shell, section, layer shell, and of course you can create many layers. Now in this case, I just want to create 3 of them, but of course probably you need more of them. When you say the first one, the second one, and the third one. So you have the first brick, then some material in between, and then another brick. And then you assign the same number of layers with their thicknesses. Now the only problem is that this is fine as far as you can assume that there is no slip between the 2 layers of bricks, okay? Instead, if you want to model that behavior, a shell is not suitable. So you can either do it with solids, and you can use our material model for doing that, or you can use 2 different shells with some nonlinear connection in between, okay? So keep in mind that when you use a shell like this, you can have this kind of composite material, but the assumption that the cross-section will remain flat is still there. It is inside the kinematics of the shell. So you cannot do it. You cannot do that if you expect the two layers to slip from one another, okay? Okay, let me remove these ones. Okay, there is another question. Can I say compression capacity? Okay, of course you can, but now I overwritten the files, but let me show you. Of course you can. I hope I have the previous file already run. Okay, so this one was the output coming from this model with the infill. Now let me remove all these files, all these outputs. And let's just take this one. I remove all the others, and I will show you how to load it with a different file. So this one, I detach this one from the database, so it will not change. Now I remove this database, or I simply open another database. And let's see if I have one without the infill. I have just with this one, I have to run the same without infill. So let me go back. Let me go back to the analysis, save. And now I want to open the other one. I think it was this one, the one that I have to send you, yes. Let me run the analysis. Oh, just not to overlap it, I want to change the name of the recorder. So I have different files. No infill. Let's run the analysis. It will take just 2 minutes. In the meantime, there is another question by Nizar. It means that we can't model mortar in shell. Of course, you can model mortar in shell elements. I'm just saying that if you want to model a shell which has some kind of infill along the thickness, you can do it. But if you expect this infill to be completely different and you expect a shear deformation between the two layers of shell, that cannot be modeled with shell, okay? So for example, if you want to model a cavity wall, a wall with a cavity, if you model that cavity just with a single shell using different layers of material, for example, our brick, and then inside you put a void material, for example, that material will be is like a rigid material in the sense that the two layers cannot create a shear deformation like this. Let me give you a brief example. I can use the annotation. Now imagine this one is my shell in 3D, okay? This one is the midplane of the shell, and this one is my wall. So let's say I have one layer here of bricks and mortar, but this is the one layer, first layer. A second layer here, and then I have a cavity here, or some infill, which is a different material, okay? Now if you look at this one, so I draw it in 2D. This is the undeformed shape, okay? What the shell does is that if it bends, the assumption is that the face will remain flat. So it is fine if this one has more or less the same stiffness of this, but if this one is very soft with respect to the other, you will have some deformation like this one. And this one is not available in any shell. I mean, any shell is called first order shear deformation theory, because they assume that the shear deformation is constant because of the fact that the section remains flat. For example, if I have plastic joints instead of ordinary mortar. No, I mean, you can model mortar with shell if you do something like this, for example. If you have bricks and mortars here, of course you can model the mortar because you're modeling the mortar in the plane of the shell. I'm talking about modeling some sort of mortar or soft material along the thickness of the shell. Those are two different things. You can do this as I did in many other examples, but you cannot do this one. Request for webinar. It will be good if you can arrange a webinar related to modeling FRP sheet strip strengthen RC members like columns, beams, and beam column joints by using shell element material for FP. Yeah, it could be done. So some detailed modeling. Okay, we can take it into account. Okay, so this one, I have to clear all drawings. Okay. So now I can go in the post processor and I can open the file without infill. So I go in surface color map as I did before, show nodes, hide beams, I select this one, and I extract the data, not from the Gauss point, sorry, but from nodes. Actually, I don't think there are so many differences in this case because the first walls died at the very beginning. So time step ID, displacement along the X, node 38, and this one is UZ field. I don't want to create an extra chart because I can overload, put it up here. So add the one without the infill. So you can compare it and you can see the differences. Okay. So keep in mind that whenever you extract a chart data, it is not mandatory to create a chart because you can create a chart just for the first time, and then the other times you just add extra. For example, you can remove it. Okay, you can add it again. Okay. So you can combine them inside the same plot. Okay, so this one was for the overlapping of the results, comparison of the results. Let me see if there are other questions here. Is there any other question? I think we have other 10 minutes at most. Okay, so if there is no other question, I would like to thank you for taking part to this webinar. As I said, you will receive an email just when the next STKO version will be available, but it will be, I think, on Monday. In any case, in the next week. So you can just download it and you can just keep on using the new version of OpenSees, either with a new trial license or if you have both a educational license, that license will be moved automatically on the new STKO. And from then on, you will be notified directly by STKO for any new upgrade. Okay. And then also by the next week, you will have all these files that I did today and the video recordings on our website. As I told you, we will put it online by Monday because you cannot use now with the actual version of STKO. This new element will be available in the new STKO version. Okay. So thank you to everyone, and see you on the next webinar. Next webinar will be on seismic isolation. Thank you, everyone.